Okay, next. Part 2, I suppose. I noticed that I'd forgotten that there already were updated um, analysis video. That was from my 2200 just this past fall. Yeah, I guess so. But anyway, I got started, so I'll finish up. So we got into where we got all the table here filled in. We've done a fit. We've gone over how to construct a chi-square. So now it's about going over why we bothered. So what happens is that the sum of the chi-square enables us to come up with a plus minus on the slope. And look at that. So the way it's defined is, this graph should look familiar for the sum of the red squared. And so now there's a graph like this for the slope and the y-intercept. So when we construct the sum of the chi-squares, then there's an official definition for the plus minus on the slope, and it's simply how much do you vary the slope so that the sum of the chi-square equals the original best fit sum plus 1. And it turns out that this shape here, this parabola, isn't guaranteed to be an exact parabola, but when you're this close to the answer, the value that minimizes it, it's safe to assume it's a symmetric parabola. And the reason being is that it's a little difficult to determine both the plus a and the minus a, and we're just going to get one of them, because what will happen is that the fit will randomly produce the plus a or the minus a, and we don't have any control over that. But if we assume that it's symmetric, then we just, whatever we get for the extreme value is what we'll say is both. This is the same for both. It's either the positive or negative. You'll see in a minute. Okay. So let's zoom in on this. It didn't work. That was weird. All right. So we've got our best fit slope here. So we're going to copy that, and we're going to paste it here. See the little number, paste value. And notice it's got all these digits here. And I suppose if it's 9.9, then 18.1 is probably okay. Yeah, even if I allow more decimal places, it would be 1801. Okay, so now what we want to do is we want to go to the sum of the chi-square here. And we need that number. And I'm not exactly certain if it's going to paste. I'm just going to hedge my bets, and I copied it, and now I pasted it as a number. And in fact, this is the one we care more about with the rounding. So we go to data, solver, and now the value of, and in this case that would be 3, because we're adding 1 to it. 3.1, and 333. I think that is good enough for government work. And now we only want to vary the slope, not the y-intercept as well. There we go. And let's hit solve. And let's see, it doesn't seem to have gone nuts. All right, so this is an extreme value here. And then, so we're going to take this and we're going to copy it. And we're going to paste number. And then to get the plus minus is we're going to say equals the absolute value of, oh, I didn't put an equal sign there, did I? Equals absolute of the extreme, doesn't matter what order you put them in, minus the central value, the best fit value. And there's my plus minus on my slope. And then, let's see. Oh, we can just, this is sweet. We can just copy this. And, well, I suppose I want the best fit. No, yeah, notice this. See, it's exactly one difference. Isn't that sweet? Okay. And so let's just get the best fit back. We can't hit the undo button. Minimize that, and we just want to change the slope again. And there it is, restored back. And we have our plus minus. So let's make it nice and neat with borders. Okay, now let's see what our calculated E over M is. And remember, this is constant voltage, so we need the, oh, this is, yeah, 160 volts, okay. So that's B3. All right, and where is it here? Okay. Equals, let's see, let's just use parentheses, always a good idea. 2 times B3 times the slope squared. Remember, that's what A is, the slope. And divided by the K value, which is here. And we don't need dollar signs because we're not using the fill handle. And, yeah, oh, square it. All right. Value. Ooh, why doesn't it like it? All right. I said, oh, did I mean, let's see. No, it's B3. Oh, I clicked on the K. It's C3, not C2. Nice. I clicked on the name instead of the number. Whoa, not bad, huh? Okay. And so standard, you take the difference divided by the average of the two values times 100 to get the percent difference. And even in the real world, you might want to say that. You could show people, look, my new number is a certain amount different, 0.53%. But so people aren't going to really, they're going to say, well, great, but let's see what is our percent error, because that's the most important thing. So our percent error is, remember, the value, the plus minus divided by the value times 100. So equals the plus minus divided by the best value and times 100, hit enter, and 1.68%. So our percent error is a little bit larger, well, 3 times larger, but you know, that's what they say, lies, damned lies in statistics. And you say, oh, well, it's 3 times larger, but when it's the difference between 0.53% and 1.68%, that's pretty damn good, getting a 1.68% error. So one would have nothing to be ashamed of here. And yeah, I mean, if we were, wouldn't make up for a publishable paper because we haven't really shown anything special, but at least we've said that we can do the experiment just as well as anybody else. Okay, so I will put this up, but yeah, you guys, the existing videos should get the job done, but with some of the questions I was getting, I thought I'd redo this. Okie dokie. We'll see you soon. So in the vein of the never-ending struggle, I realized that I did the percent error slightly incorrectly. So let's first of all, we need to move this up. And in fact, I'm just going to delete that, because what I forgot to do is and it probably isn't going to change it much, but let's see what happens. I use the values of the slope and the plus minus on the slope, but I need to get a plus minus on the of the E over M. And in fact, I need to move that up even more over. So plus minus E over M. And once again, when I just put the plus minus, I have to put an apostrophe so I don't confuse Excel. And so we need the extreme value. So this is, we use this again. So equals 2 times whatever the voltage, the constant voltage is 160. And then let's see, times now we want to use the extreme slope. Yep. And that would be squared, yep. And then we have to divide it by the k squared. Okay. All right, so this is going to give us, then we say equals the absolute value of the difference between these two guys. And that's our plus minus. Oops, certainly want to put that into psi naught. There we go. See, it's 2 orders of magnitude smaller. So now we get this. So this equals the plus minus divided by the measured, the actual value, and then times 100. And okay, it did go up a little bit to 3.66%. So it's not as nice as before, but that's still pretty darn good. But of course, again, we haven't really demonstrated, since we're so very close to the number previously measured, if you will, as opposed to the accepted, which it's better to think of previously measured. We haven't really proven anything because our percent error is bigger than the percent difference, but our percent error is still pretty good. Okay, so now I got to re-upload this video.